Okay, lesson 5.6 is the last one of the unit. We're going to talk today about definite integrals, how to use the calculator to do the integration, and another part of the fundamental theorem of calculus. So the difference here with a definite integral is it is written with upper and lower limits. See this a and b? So it's attached to this integration symbol, and really this whole integration symbol can be thought of as signed area. So imagine me saying I've got a function f of x, we're going from a to b, and it's the area underneath that curve and above the x-axis. Okay. In this case the value is positive. It could be below, so it could be negative, or it could be 0, where the two sides kind of match up to be the same. So unlike previous integration processes which produce an indefinite integral, this time a definite integral represents a number value because it's really talking about the area. So we can use a calculator to help us with that, and there are two ways to do this. There's one in the calculate menu or one in the math menu. So I'm going to show you both of these ways. And if you can take your graphing calculator out, that would be great. So let's just take a look. We can actually graph out the function. So go y equals 2. Let's clear all this stuff. I will say x cubed minus 6x. I'll go zoom standard. And if I ask you now to find the integral from -3 to 1, I can use this calculate feature, that second trace, and choose number 7. My lower limit is my a value, so I'll type in -3. My higher limit is 1. I'll type that in, and look what it does. It shades things in, and it tells you that this whole integral is 4. So the answer here is 4. Okay? Can you try number 2 on your own, please? Choose number 7 again. -√6, lower limit, √6, upper limit, integral 0. And finally, try the last one on your own. Absolute value this time. So go math, number, choose 1, absolute value of x cubed minus 6x. Notice what happens when I graph that out now. Everything gets, reflected above. And now, if I were to use the calculate feature again, from -5 to 5, you'll see I get a crazy answer. Yeah, here it comes. Excuse me, 198.501. And so that's how we use the calculate menu through the graph. We can also use the math menu on our calculator to do the same thing. And in the math menu, the calculation here menu, we can use this notation called FNINT. So to find that feature on the calculator, you go to math and scroll down to number 9. So this is math key on the calculator, number 9. And you can type it in this way. So notice that the first thing is always the function. X is always x, which is the variable. And then here's your a value, and here's your b value. Okay? So try this with the math menu. And you just need to be aware of how you can calculate these things using both ways. X cubed minus 6x, close the bracket, comma, x, comma, -5, comma, 5. Takes a bit of time, but you'll get the same answer. what it tells you. There we go. 198.50. Well, it's a little bit different, right? 198.500. Okay. Just to let you know, this math menu gives a more accurate answer because it's not using a graph to approximate. So I would prefer if you actually use this method here to do these calculations if I ever ask you with the calculator. Okay? Alright. Now, you know how to calculate these things with a calculator. What happens if you don't have a calculator? So let's use the let's use the idea of signed area to evaluate this integral. Okay? So notice in this particular example, this is the absolute value of 2x minus 1. So maybe you remember how to graph this out, right? This is 1/2 as the breakpoint. We have a V-shaped graph. I'm going from 0 to 3, so 0 to like 3. And if I ask you to think about signed area, I hope you can see that this is actually two separate triangles added together. And that would be the signed area here. So I can say that the integral from 0 to 3 of the absolute value of 2x minus 1 dx is equal to our first triangle, which is 1/2 as the base. And the height at 0 would be what? 1, is it? Because 2 times 0 minus 1 is -1. The absolute value of -1 is 1. So 1/2 times 1 divided by 2. And over here, my triangle, I'll put in green. The distance there is 2.5, so 2.5 times, now the height here, 2 times 3 is 6, minus 1 is 5, and also divide that by 2. So ultimately we have here 1/4. Ultimately we have here 5 over 2, 25, 25 over 4. So the solution here is just 26 over 4, or 13 over 2. And that's how you can do it geometrically without a calculator. Okay, let's turn the page. So if I gave you a picture like number 6 and I said, can you set up a definite integral? Can you actually write that integral notation for me? So notice it's the integral of the function 2x squared minus 3x plus 2 with a dx. But this time, to make it a definite integral, we need values of a and b. So where does it start and where does it end? How about at 0 and ending at 2? Ta-da. Okay, now you might be thinking, this is great, Mr. Lee, but we need to find an algebraic way of doing this. Fair enough, okay? I'm going to ignore this part here, and I want us to turn to our supplemental page. Okay, so if you can go to your 5.6 supplement in the back of the book, I want us to take a look at this investigation to help us figure out a way to do this algebraically. Okay. Now we've seen something like this before. And don't write this down, before I asked you to go from the integral from 0 to x of f of t dt. This time, however, I'm saying let's start at 3 and go to x of the same function, so this is still f of t equals to 2t. But this time now, notice I'm keeping the lower limit at 3, but I'm changing my upper limit. So instead of finding the area of the triangle, I'm now trying to find the area of this trapezoid. Okay, so let's try and figure this out. Okay, so if I said the upper limit was 5, that means I'm asking you to do this, the integral of 3 to 5 of 2t dt. How would you actually do this? Well, if I draw a picture out here, once again, notice that I'm going now from 3 to 5. And ultimately, if you think about how I can calculate this, is I can use two triangles, this larger triangle, and I'm going to subtract from that the smaller one. So if I take the larger triangle, the base would be 5. The height, because it's 2t, is 10. And I'm going to divide that by 2. And I'm going to subtract from that the smaller triangle, which just happens to be 3 times 6 divided by 2. Doing these calculations, it's 25. This is 9, so 25 minus 9 gives me this area, which is 16. Okay? Can you try the next one, please, on your own? And let's see what you get. you get this answer, 64 minus 9, which just gives you 55. Cool. Now what if I generalize this to x now? So don't know what x actually is, but nonetheless I can still find the area, because the area of the larger triangle will be x, the base, times 2x, which is the height, divided by 2. And the area of that small triangle still stays the same, it's still 9. So hopefully you'll see that this is equal to x squared minus 9. So ultimately, if I actually ask you to calculate this integral from 3 to x of 2t dt using this rule, you found that the g of x function is actually x squared minus 9. And my question is, what do you notice about this number you keep subtracting? 9, 9, 9. Hopefully you can realize that 9 is that constant that represents the small triangle. That we are subtracting each time, because we really don't want to include that area. And if you think about how you get that 9, well, the 9 comes from doing what? Comes from plugging in 3 into the antiderivative of 2t, which of course just becomes t squared. So hopefully you can now visualize and see what's going on. If you have both upper and lower limits of the integration and both of them are constants, what you're actually doing is you're going to find the antiderivative of the function. I'm going to use capital to represent that. And you're going to evaluate it by plugging in the upper limit and subtracting it from the lower limit. So note, I'll say capital F of t represents the antiderivative of little f of t. Sometimes people will write it also like this. Just go f of x in this case, capital F of x, and they'll say evaluate from x equals to b when x equals to a. Or sometimes people will be even more simplified and just go ba like that. Okay. Now, if you're curious about why that works, let me just give you a quick proof. So remember that if I call a of x the area of the region bounded by the curve from x equals to a to x equals to x. So imagine this area here that I'm shading in, that whole thing represents a of x. Okay? Of course, this is a function y equals f of x. We also know that if I were to plug in a, that means I want an area from a to a. Well, what kind of area do you have there? It's pretty much nothing. Okay. Now, if we introduce this idea that capital F of x as an antiderivative of little f of x, we can also say that the area of x, so that's that big picture up here, is equal to the f of x plus c, where c is a constant. Okay. Remember that idea of plus c as an indefinite interval? Now, if I were to substitute x equals to a, so a of a equals to f of a plus c. What did you just say f of a of a was? This was equal to 0, yes. So 0 equals to f of a plus c. And if I ask you to solve for c, then c just equals to negative f of a. And if I were to now substitute it back into this original equation here, a of x equals f of x plus c, then what you've just told me here is you have a of x equals to f of x, and instead of plus c, the plus c becomes, minus f of a. And more commonly, sometimes instead of using x, they'll say, hey, this is b, your upper limit. And that's why we can rewrite this with b as your upper limit as well. and then get, see, f of b minus f of a. So more commonly written with the upper limit set to b, you really have the following. This integral of a to b of f of x dx is just equal to capital F of b minus f of a. And once again, this is called the definite integral. And f of b, f of a, this f, of course, capital F is the antiderivative. All right. So if you know this rule, then we can now use this to help us calculate these definite integrals algebraically. All we need to do is find the antiderivative and then plug in the upper limit, evaluate, plug in the lower limit, evaluate, and then subtract. And that's what this says here. This is the second or the first part of the fundamental theorem calculus. So let's go back to our notes now and let's try some examples. So let's skip this 7, 8, 9. And let's go all the way to number 10. And there we have it. In the box again is our lovely fundamental theorem of calculus. So let's try 10, 11, and 12. So what's the first thing we need to do? Did you say find the antiderivative? You bet. But before I do that, let me just rewrite this nicer. I see this ugly root. So I'm going to rewrite this as 2y to the 1/2 plus 1. And then yes, let's go ahead and find the antiderivative. So the antiderivative of y to the 1/2 is y to the 3/2 divided by 2/3 with a 2 in front, so that'll be 4/3. And the antiderivative of 1 is just y. And it's this whole expression, which is your antiderivative, that we now have to evaluate from 0 to 4. So we plug in 4. Okay. And we also plug in 0, just so happens to be 0. And then we subtract them. And so in this case, if you did the calculations, for power 3 over 2 is 8. So this is 32 over 3 plus 4. That's 32 over 3 plus 12 over 3. How about 44 over 3? Okay. All right. Let's try 11. Ooh, I see some u substitution. Let u equals to, actually you don't need to use, well, okay, I'll do it anyways. 4t plus 1 du dx equals to 4, oops, it's not du dx, it's du dt, thank you. So du equals to 4 dt, or dt equals to du over 4. So you can rewrite this as 1/4 the integral of u to the power of 5 dt. That gives us 1/4 u to the 6 over 6, which is just 1 over 24 u to the 6. Now put the u back in now, 4t plus 1 to the power of 6. And this whole thing gets evaluated from 1 to 0. And by plugging this in, 4 times 1 is 4 plus 1 is 5, 5 to the power of 6. Whoa. So this is just really 1 over 24. I can factor that out. 5 to the power of 6. Then I'll plug in 1. 0. 4 times 0 is 0 plus 1 is 1. 1 to the power of 6. So that's minus 1 to the power of 6. And I'll leave my answer like that, because I don't have a calculator. Okay. Number 12, same business. This time I'm thinking, yeah, to find the antiderivative, hello, u substitution again. Let u equals to 2x minus 1. I think that would be good. Du dx this time is 2. So dx is just du over 2. Now, if I were to replace this now, I get the integral, and notice it's root u, but I still have this x here. So hopefully you can see that I can go ahead and maybe solve for x. U plus 1 equals to 2x. So x equals to u plus 1 over 2. So I have a u plus 1 over 2. And then here, instead of dx, I have du over 2. So trying to simplify this, I'll take out the 1/2 and 1/2, will be 1/4. And now I have u plus 1 over root u. Nice. Now I can simplify this even further and say this is the integral from u divided by root u is just root u. And then this would be 1 over root u. And if you want to save some space, then we just rewrite that as u to the power of 1/2 plus u to the power of negative 1/2 du. Now, you see how I left out the integral limits? So in the previous one, I left them out and then I just put them back in after I resubstituted. Well, you don't necessarily have to do that. If you want to just leave everything in terms of u, then why don't you just rewrite these limits in terms of u as well? So if I were to use this expression and evaluate, if I plug in 1, 2 times 1 is 2, minus 1 is 1, my lower limit is still 1. And if I plug in 5, 2 times 5 is 10, minus 1 is 9, my upper limit is now 9. Doing that, I don't need to now substitute in later on. Alright, so let's take a look at this now. Anti-differentiate to get the antiderivative, u to the 3/2, 2/3, u to the 1/2 with a 2. Evaluate all of this from 9 to 1. Let's see what we get. 9, 3, 27, so that's 2/3 times 27. That's just 3, 6. Subtract that 1, so 2/3 plus 2. 18 plus 6 is 24, so this is 1/4 times 24. 2/3 plus 2, that's 6/3, that's 8/3, minus 8/3. It's looking ugly. 24. That's what? Is it really 24? That seems like a lot. 9 square root 3 is 27. 27 2/3. 27 2/3. That's not 24, is it? And that's only 18. But 18 plus 6 does look like 24. Alright. Okay. 72 minus 8 is 64. So this is 1/4 times 64 over 3. And that just simplifies to 16 over 13. Cool. Now, one application of this, and this is the last thing we'll do today. This is very important. I've seen this so many times on the AP exam. I can take that expression and then rewrite it as follows. See how I just took this and stuck it on the side? So f of b is like your upper limit, but it also could be like your ending value. And f of a is like your starting value. And to get from the start to the end, you have to add some sort of what I call accumulation. So that's why this is called the start plus accumulation method. This means a function value can also be found as a starting value plus its definite integral. So looking at this one, f of 2, I want to find the final value f of 2. That's equal to the starting value f of 0 plus the integral from 0 to 2 of the derivative function. See that? So just go ahead and do the antiderivative. This will be x cubed plus 3x. Evaluate this from 0 to 2. 8 plus 6 minus 0 plus 0. That's just 14. And then just add this to your original y value, which is 4. And look what you've got. Your answer is 18. Okay? And so for the next one, we can talk about velocity and position. Remember this stuff? Velocity is the derivative, so the position at 3 will be equal to the position at 2 plus the accumulation of all that distance from 2 to 3 of the velocity function 2 to the power of t dt. This you'll have to calculate with the calculator. So once again, an opportunity to use FNINT. Math 9, 2 to the power of x, comma, x, comma 2, comma 3. 5.770. So 8 plus 5.770 gives you 13.770. Done.